So for students in Randolph, Jason's office hours are posted here, and feel free to use, seek out help from him in person. There's a lot of days, I'm only down on Monday for class time, so he's taught this class many times before, and he can be a good resource for you. Also, you have until Monday, if you so choose, to turn in assignment 2. I haven't changed it on Canvas yet, but I'm going to. If you notice it hasn't changed, feel free to send me a reminder. Sometimes I need those, and I'll fix that. Part of the reason is I still don't have assignment 1 graded. I've kind of failed my own deadline that I set for myself of having it done within a week. Not making excuses. It's my responsibility to get it done. I've had a family member in the hospital for a couple of weeks, so that's been taking up my evenings, which is why I haven't put as much time into this as I usually can. So you'll have till Monday to turn in assignment 2. We're going to finish up equivalence relations, and then if we have time, get started on functions. I do have an assignment 3 ready to go, and then so I'll probably wait until Monday. I'll probably post it by Friday because it is ready to go, and maybe have it due maybe a week from Monday, just so we have enough time to do it, to work on it. Before we pick up where we left off, who's got questions?
Can we go over number 2 on the homework?
On the assignment?
You do 3 after that. I'm.
Yeah, 3.
Hold on.
More explanation.
Let me see if I'll just let me bring it up on Canvas so I can see it. So 2, oh, okay, yeah. All right, so we've got a relation S on the integers, which we're defining by saying x and y are related. It says if there's a prime number p such that p divides x and p divides y. So in number 2, we're saying S is a relation on Z. And x is related to y. I'm going to use that notation. I find it convenient. X is related to y if x and y share a prime divisor, is basically what that says.
Does it depend on land?
Yeah. So that they're just defining what it means to share, to be related. So, can somebody give me some integers that are related under this definition?
3 and 6.
3 and 6, yeah, 3 divides 6. So they share the prime divisor, right? 3 is related to 6 because 3 divides 3 and 3 divides 6. There's their prime divisor. It's not that x doesn't have to divide y, but they just have to have a factor in common. So for example, 6 is related to 27 because 3 divides, with the same prime, right? 3 divides 6 and 3 divides 27. So in this problem, they ask us to see what properties hold. So the first property that we usually look at is reflexive. What do we think about that?
Does that mean like a number relates to itself?
Yeah. Is every integer related to itself?
I would say yes.
Yeah, you know what? That is my instinct too. Can you explain why you think yes?
I think yes, because you could say that a number divides itself, but then you can also flip it around and say that the number divides itself, and if both hold true, then it's true.
Well, it's not about x divides y. It's about, does it share a common prime divisor? I mean, a number divides itself for sure, always, but
So if x is equal to y, then they both share a prime divisor. Period.
you think so?
I tend to be wrong. Yeah, I do.
So this is a tricky question. So like it feels right, you know? And as it turns out, it's not reflexive because you can find a counterexample. You can find two counterexamples. And only two, really.
Is 1
Yeah.
part of it?
One is, so that's the question. Is one related to one? And to answer that, we have to understand what a prime number is. Everybody knows part of the definition of a prime number.
That wouldn't be in the.
One's not a prime number, is it?
One is not prime. Yeah. One, everybody knows part of the like the kind of what we think of as the important part of the definition of a prime number. Number's prime if its only divisors are one in itself, and it would appear that one fits that definition. But if you look up the definition of a prime number, it says a prime is a positive integer greater than 1 whose only divisors are 1 in itself.
Gotcha. Because if one were a prime, then every other prime number would have two prime divisors.
Yeah, like it would disrupt what it means to be. Well, here's what it would disrupt. Up until a few hundred years ago, mathematicians did consider one to be prime, for the reason you think. Its only divisors are 1 in itself. But there's a really important, theorem in mathematics called the fundamental theorem of arithmetic, which says, and we're going to talk about this later, but it says that every number is either prime, right? Every number is either prime. Every positive integer greater than 1 is either going to be prime, or it can be factored as the product of primes in a unique way. That's really important, in a unique way. So 12 is not prime, right? But we could make a factor tree and get its prime factorization. So 12 is 2 times 2 times 3, or 2 squared times 3. That's its prime factorization. It's 2 2's and a 3. That's like its molecular structure. It's what defines 12 as a number in the integers, really, when we think about like number theory and stuff. It is the only number that's defined by 2 2's and a 3, right? Like that is its definition almost as a number. If one's considered prime, then the factorization is no longer unique, because 12 would also be 2 squared times 3 times 1. There's another prime factorization. 2 squared times 3 times 1 squared. There's another prime factorization. So the integers are what we call a unique factorization domain. The fact that positive integers factor in a unique way is fundamental to like the underpinnings of number theory. That's why 1's not considered prime. It's problematic if one's considered. So 1 is just like a special number that is neither prime nor composite. So it's kind of a trick. It feels like a trick question because we have to think about what it means to be prime. I like the thinking, though, that says, oh, obviously a number shares a prime divisor with itself. And if you included that and stated that it was reflexive, I wouldn't take off points. I would just write a little note saying, actually, it's not because of this. And, that feels like a trick, but not trying to be tricky. So there's the reflexiveness or non-reflexiveness, I guess, of this relation.
Wait a minute, you said that there were two examples.
Negative one
Negative one?
is the other one.
So hang on a second.
Oh, right.
Would 1 even be in the set, though? Because if 1's not a prime, then it doesn't share a prime divisor with anything.
Yeah, that's my point. There's a counterexample that shows that it is not reflexive. So this question right here gets a no. 1 is in the integers, but S, the relation S, does not contain the pair 1, 1. Right? So I said 1, S1. I was using this notation, but another way to write that is to say that 1, 1 is not in the relation S.
Yeah, I think I'm like on the same line as you. Like all the numbers are in there, but there's only a relation between X and Y if there's that prime divisor.
Yeah, like so it's a relation on all the integers. So the set we're working is all integers. 1 is in there. Because 1 is included in the integers, that's what makes this relation not reflexive. The ordered pair 1, 1.
S on Z by XY is an element of S if and only if there is a prime number P such that Px and P divides Y.
Yeah.
So, if 1, 1's not in the set, then what are we evaluating exactly?
1 is in the set of integers. So capital S is the relation. Right? Instead of calling it capital R, I called it capital S. It's not a relation on a set S. Like S is the relation itself.
Right, but we're determining which one of these properties S has.
Yeah, I know. The relation's not reflexive because I can find an integer that is not related to itself. That integer is 1. 1 is not related to 1 because 1 does not share a prime divisor with itself because 1 has no prime divisors.
Okay. If I'm the only person who's hung up on this, then we can totally move on and I'll just catch up with you at some other point.
The dog looks confused.
What? I want to give other people an opportunity to chime in on this.
The way I understand it is like you have Z, right, which is all of those integers.
Yep.
And then you're saying that there's a relation S that has properties. So then you're trying to figure out if one of those properties is reflexivity, which you can say S doesn't have the reflexive property because consider 1.
Yes.
Instead of Z, but it can't be reflexive because 1 is in the original set.
Right. 1 is in the set of integers. But the ordered pair 1, 1 is not in the relation. Right? 1 is not related to itself. It has no prime divisors to share with itself. There does not exist. You can't find me the prime P. Yeah, okay.
I get that part. I just am hung up on what defines this set, I guess, which I thought I had my head wrapped around, but I guess not.
So the set that we're working with is the integers. The S is the relation, is how we define whether two integers are related. So for example, 3 is related to 6 because they share a prime divisor of 3. 6 is related to 27 because they share a prime divisor of 3. Or, 12 is related to 56. They share a prime divisor of 2.
And all of those numbers that you just said are in the relation S.
No, all of the numbers, 12, 56, 6, 27, 3, 6, they're all in the set of integers. So don't use, we think of a relation, the set that this relation is on is the integers. Here's our set right there, just the integers. The relation S, we could think of also as a set because it's a set of ordered pairs, right? It's a subset of Z cross Z.
Which is why I keep calling it a set.
And that's fine, but just don't conflate the set S, which contains ordered pairs, with the set Z, which just contains the integers. Like S and Z are not the same set.
I get that.
Okay.
I just thought we were evaluating S.
We are, yeah.
Lack of a prime divisor shared between the two elements of every relation in S. It qualifies one from being in S.
Yeah.
That's where I'm hung up.
You don't. You're hung up on why 1, 1 is not in S?
Or why that disqualifies S from being reflexive because
to be reflexive, every element of Z would have to be related to itself. No matter what integer.
S had to be related to itself.
No. Oh, no. The S is a relation on Z. So when we talk about elements of S, the set S, we're talking about
the elements of the parent set.
Yes, we're saying what's related. So 3 is related to 6, and we're thinking of 3 is not an S, 6 is not an S. These guys are in Z. Right? It's elements of Z that are related to each other.
Okay. Thank you.
Okay.
I think I get it
Good.
now.
Good.
But the pair
36 is in S, though.
The pair 3, 6 is an S. Yeah. Can somebody find a pair that's not in the set? That's not related. Like a pair of integers not related to each other.
5 and 2.
What?
5 and 2.
5 and 2. They don't share. I mean, pick any two different primes. Damn, you definitely got it. Or any even number and any odd number won't be related to each other, right? So it's not too hard to find pairs that are not related. The whole thing about it not being reflexive is a subtlety about what primes are. So if we think about the next property that we usually get to is symmetric. Do you think this relation is symmetric? Andrew is nodding his head yes. Andrew, do you want to explain why you think it's symmetric?
Yeah, so if 6, 9 is in S, they both share the same prime factor of 3. That would mean that 9, 6 is also in the set.
Okay, can you explain why you think it's symmetric without only relying on an example? Because an example is not a proof. I like your reasoning, right? So Andrew started by saying, well, 6 is related to 9 because the prime divisor there is 3. And so that means 9, and notice the 9 has to be related to 6 because that prime is also 3. Can we write an argument or come up with an explanation that doesn't rely solely? It's good to including examples can bolster your explanation, like that can be illustrative for the reader, but we need something more than just an example. So usually if we're trying to show something symmetric, we might start by saying suppose
Rachel,
X is related to Y. Yeah.
can I take a whack at this?
Yeah.
An example, because this is something I struggled with last semester too. So if the relation A, B is an element of S to the minus 1, I'm not sure how you say it. And P divides A, then P divides B.
Yeah, only it's not the inverse relation, it's just the relation itself. So you're saying, let's suppose A is related to B, right?
But the inverse relation is the symmetry of the original, right?
Well, it's the relation you get if you just reverse them all. I guess if something's symmetric, if a relation's symmetric, then the relation is equal to its inverse relation, right? Because you have all the reverse pairs in them. But we don't usually invoke the inverse relation when we do this. If A is related to B, if we say suppose A is related to B, we want to explain and then be able to say then B is related to A. So what does it mean to say A is related to B?
They share a prime divisor or prime factor.
So they share a prime divisor.
Really sharing is like the root of the proof, right?
Yeah. Or there's a P that divides both A and both B, right? Or share a prime divisor. However you want to word it is fine. If A and B share a prime divisor, what can we say?
It's
Then B and A also.
Then B and A share a prime divisor, right? Sharing a prime divisor is a very symmetric relationship to have. 3 and 12 and 12 and 3. If I write those numbers in a different order, it doesn't change what prime divisors they have, and it certainly doesn't change whether or not they share a prime divisor. So
I guess why is it not proper to invoke the inverse relation to illustrate that? Because that's what I was trying to get across through invoking the inverse relation.
I mean, if you invoke the inverse, certainly the inverse relation exists, but we can't just say the inverse relation is equal to the relation. That would be saying it's symmetric because it's symmetric. It would be a circular argument. You still need to conclude by starting with this if and then concluding with that then. That would then allow us to say that S is equal to S inverse, So you could kind of make reference to the inverse relation, but in order to say that S and S inverse are the same, you have to make the same argument. We don't get around being able to say, making the argument that if AB is an S, then BA must be an S. It is confusing. Like, I get that, when we learn to write arguments, it's hard because we're being quite rigorous here. And we have to be really careful about the things we assume, and we need a reason to say everything. We need to be able to back up everything we say. And there's a lot of as people kind of start this process, there's a lot of circular arguments that people start writing. I mean, I write these comments all the time when I'm reading over arguments. And that's okay. I learned to write mathematically by getting back papers that were just smothered in red ink. I don't know how to describe it, but it was getting a lot of feedback and then reading a lot of examples. So it does take a little bit of patience and perseverance, but it happens. It's a skill that we build. So do we feel like we have a handle on this relation in number 2? And kind of take it away with the other. If you write a draft and you want some feedback on it, feel free to send it to me before you turn it in. That's fine. Okay. Number 3, people asked about. Oh, that's a good one, I think. Right? All right. Okay. So we want, so it refers you to exercise 24 of the practice exercises. Did anybody take a look at that?
Yeah, I looked at the answer.
Okay, good. Did it help at all? No help at all. So, okay. So we have a Boolean algebra, and the first thing we do is we define what an atom is of a Boolean algebra.
What's confusing me is this little symbol that they're using for relation, this less than, equal to.
Mm-hmm.
Is that what they actually mean? That this value is
Nope.
less than or equal to? Or
No, it's sort of like when we were looking at partial orderings before, and they made a little remark that was actually people often just use the less than or equal to symbol as to denote what that partial order is.
So is there any contextual relationship at all to it being less than or equal to anything? Are we just throwing that definition of that symbol out the window here?
We're not throwing anything out the window. What you have to understand is that we're learning a different kind of math. I mean, we don't make up a new symbol for every little thing that we do. We do sometimes. For example, you'll note that when we talk about sets being contained in other sets, we were a little queasy about using the less than or equal to symbol. So instead we said, let's make it curved. Nobody will notice. Okay? But it's the same kind of relation.
Sense, though, because it's a C and contain.
Does
You
it?
see some correlation? I mean, I saw the correlation.
Okay, all right. So what I'm gonna do with us for problem 3 today is get us so that I think we understand what it means to be an atom and contextualize what we think we're trying to prove, right? Or what we are trying to prove. Which should get us, I think, a kind of a start on this. So B is a Boolean algebra. X is an atom if for all y and b, y related to x implies that y is equal to 0 or y is equal to x. The relation is that, oh, okay, you're going to understand this relation really well. It's going to be like clear. It's going to be almost intuitive by the time we're done, I think. I know those are bold words. So we define the relation. I guess this could have come above, but we define a relation on B by the following. X is related to Y if and only if xy is equal to x. So whenever you are working with a Boolean algebra statement, equation, whatever, and you're having a hard time like understanding what does this even mean, is it meaningless? So understand that sets and their subsets, like if you take some set X and look at all of its subsets, right? Those subsets, like the power set of X, with the operations of union and intersection, union is our plus, intersection is our times, that's a Boolean algebra. So what they're saying here, if I were to just recontextualize what this relation means if I just think about sets, is that a set A is related to B, note the change in notation here, if A intersect B is equal to A. Does that seem true? Like, if I think about this right here, let's draw a Venn diagram for what that would mean. I'm going to draw B first. How do I have to draw A to make this true? A intersect B.
Totally inside of B, right?
Right. It would have to actually be like a subset. So they're basically just defining in a more abstract way this relation. And that's what Boolean algebra is. There are different examples of a Boolean algebra. The reason that we like to have this abstraction is that if I prove that something's true in a Boolean algebra generally, then that means I've already proved it's true for everything that is a Boolean algebra, like sets, like propositional logic is another example of a Boolean algebra. So this is what the relation is. So it's a very kind of, I would say, naturally defined relation once we contextualize it here in terms of sets. Now they've defined an atom. Let's focus on this part. So a set A, let's think about what this means. A is an atom if for all B in the power set, right? For every set B, A is a subset of B means that either A is the empty set or A is the set B itself. And I guess I should avoid using B. Let me just switch this out for C. I don't. In the problem overall, we're talking about B as being the Boolean algebra, and I just don't want us to confuse it with that. So A is an atom. So an atom is like a really small thing, right? And that's the sense that we're trying to convey. The only way A is an atom if no matter what set we pick for C, if A is contained in C, if A is a subset of C, it's either the empty set or it's the set itself. Oh, hold on. I got that backwards. This is about C. This is going to make a lot more sense now. A is an atom if the only subsets of A are the empty set and A itself. It's small. It doesn't contain anything else. Right? It's sort of that's the sense that this is trying to convey. So here's an example. We can find atoms of an actual set. Let's say our set big X contains the elements 1, 2, and 3. An atom would be the set, the subset of X that just contains, for example, 1. Because if I take any other subset here of X, like 1, 2, 3, 2, 3, 1, 2, we know there are 8 subsets of X, right? The only ones that will be subsets of this guy are this set itself, the set containing only 1, and the empty set. It's like the smallest bit, the smallest subset we can grab without, aside from grabbing the empty set itself.
Is it the length of the subset or the values within? Because you could...
Oh, it's the length. Yeah, that's not the only atom. This is an atom.
Yeah.
This is an atom. And I guess the empty set would be an atom too, right? It's like the smallest bits. The smallest way we could form a subset.
The length of the empty set is the same as the length of another set, which is just 1.
The
Or
length?
any of these.
What do you mean by length?
How many elements there are?
Oh, the size?
Yeah, size.
So the size, and of course here I've just defined a discrete set, so I'm not talking about a continuous set like the real numbers or something. Although this, I guess we could define it on the real numbers, and the singletons would just be isolated points, right? An interval with no length, right? So this is what an atom is. And what you're trying to prove now, prove that if X is an atom of B and Y is in B, then either XY is 0 or XY is X. So and Y is in B. Then either xy equals 0 or xy equals x. So for these atoms, if we think about sets, we're saying if x, if we have a set that's one of these atoms, one of these smallest ones, then if I intersect that set with any other set itself, it'll either be empty, it won't share anything in common at all, or it'll be the set itself. Like, it's either contained in the other set, right? Because it's one of these small guys, or it doesn't intersect that with that set at all. So when you prove this, you're going to start out saying, suppose X is an atom of B, and let Y be an element of B, right? We know that if X is an atom of B, and Y is in B, then if you have this relation, if Y is related to X, then either Y is equal to 0 or Y is equal to X. We might get some direction from the practice exercise. Which one was it? 24? Oh no, it's a page. Oh yeah, you said page 9. Okay. So we know that it's a partially ordered set. We know that it's symmetric. We know that it's reflexive, anti-symmetric, and transitive. That might get you some progress there. But you're going to start by saying let X be an atom and let Y be any old element of B. You know that you have this. This relation holds. You know that this is a partially ordered set. You'll probably need to refer to this at some point. If it helps you to contextualize by thinking about it in terms of sets first, then you could kind of write out what your argument would be with like some set with 3 or 4 or 5 elements or something, and then try to translate that back into the Boolean algebra. Times in a... What?
We can't use the definition of the fact that it's a partially ordered set in our argument, right?
You can use the fact that it's a partially ordered set.
So that seems like half of it right there.
Okay. Yeah, feel free to use it. You've done it in the practice exercises, or at least hopefully read the argument about it in the solutions. So hopefully this gives us at least some context and a good way to think about this problem. Don't forget that we have properties of Boolean algebra, you know, the idempotent properties, which we proved. There are some other ones that we have those axioms, you know, how a Boolean algebra is defined. You're probably going to, you know, rely on one or two of those properties.
Now, is that 0 or is that just
This is 0, the element of the Boolean algebra is 0, but if you contextualize a Boolean algebra statement in terms of thinking about sets and intersection and union, the 0 element is the empty set. I think you might want to start this by showing, by showing that the element xy, you know, if x is in B and y is in B, then xy is in B because it's closed under times. I think you're going to start by showing that xy is related to x. Don't state it, establish it. I think it starts with something like that.
What is that?
What do you mean, what is that?
What does that mean, don't state it, establish?
Don't just say this is true, so I'm going to use it. You can't use it, like, you're going to show it, like prove it, argue that this has to be the case.
Isn't it inherently the case because it's partially ordered set?
Why? I mean, I don't think that follows from being reflexive, symmetric, or reflexive, anti-symmetric, or transitive. So I don't think that's why.
You just you just defined the relation of a partially ordered set on B by x is in y if and only if x intersected with y equals x.
Uh-huh. So you're going to use this definition to show that x, y is related to x. So that's, I mean, I think that's as far as I'm going to get you today. You know, look at how the relation's defined. What would it mean to say these two things are related in that order? What do you have to look at?
And that's one of the axioms too, isn't it?
No, the axiom does not, I don't think the axiom uses this relation as it's defined.
I'm not going to ever stop being lost on this, so let's just move on.
I think that you will stop being lost on this at some point. Maybe it won't be right this moment. We start by not understanding it, you know, like learning something starts by not knowing something. So it's, you know, it's a little bit tricky, but I think we can do it. So I want to return to the notes. We had been working with equivalence relations, and an equivalence relation is a relation that is reflexive, symmetric, and transitive. We just spent a bit of time showing that this relation on the integers, which we defined by saying A is related to B if A minus B is a multiple of 5, we show that that's an equivalence relation. If we have an equivalence relation on a set, then that defines, along with that equivalence relation, it'll define a set of equivalence classes. So if I take any old element of our set and then I say, well, what are all the things in the set that are related to this under the equivalence relation? That's an equivalence class. That's the equivalence class of that element. So for example, again, we're looking at we're referring to that same relation before saying A and B are related if A minus B is a multiple of 5. So let's identify some equivalence classes. Let's start with 0. Here's how this is defined. It's the set of all x, so the equivalence class of A is the set of all x that are related to A under this relation. So this will be the set of all x in the integers, because our set is the integers here, such that x is related to 0. And this relation says x is related to 0 if x minus 0 is a multiple of 5. So if x minus 0 is a multiple of 5, that means x is a multiple of 5. All the things that are related to 0 will be multiples of 5. So there are infinitely many of them, right? There's the equivalence class of 0. If we pick a different integer, let's say 1, this is the set of all x that are related to 1 under this relation. So what that means is it's the set of all x such that x minus 1 is a multiple of 5. Now I'm going to just rewrite that equation to make it easier to figure out what elements are in here. But if I just rearrange that to solve for x, that means that in order to be related to 1, x has to be of the form x is equal to 5k plus 1. X has to be 1 more than a multiple of 5. So I just add 1 to all these elements I just wrote down in the set before. We get negative 14, negative 9, negative 4, 1, 6, 11, 16. These are all related to 1. Any integer that's related to 1 is going to be 1 more than a multiple of 5. What's that? No, we're adding 1. If you add 1 to negative 15, you get negative 14. Yeah. The equivalence class of 2. Defined analogously. Set of all x such that x minus 2 is 5k, and then for some k and z. I'm just getting tired of writing that, so I'm getting those little quotation marks. We could, again, rearrange that equation. This means that x has to be of the form 5k plus 2. What's included here?
You have 2 as an element?
2 will be an element. Yep, I'm going to write that up here. Say that again.
Negative 13, negative 8, negative 3.
Mm-hmm. And then on the other side, we got 7, 12, 17. Let's keep going.
So,
Oh, go ahead.
Would, like, the 0, 1, and 2, would that be kind of like the offset from everything? And you just add 5 pretty much from right one end, like the positive end to the negative end? It's like you use 0 as the offset, or like 1 as like the starting point?
Yeah.
And you add 5.
And then they're all 5 apart. That's what it means to be right related to 2, is that when you subtract, it's a multiple of 5. So all the elements in each equivalence class are 5 apart. And yeah, you could think of this as the offset. Also, I think of it, once I have the 0, 1, all I do is add 1, right, to keep going. So the equivalence class of 3. So these are 3 more than a multiple of 5. So we get what? Minus 12, minus 7, minus 2, and then 3, 8, 13, 18. Notice that if that number that you think of as that you kind of described as being the offset is this number itself, right? And it makes sense that 3 should be in the equivalence class of 3. It's an equivalence relation. Everything's related to itself. If I find the equivalence class of 17, 17 had better be in it, right? Let's do another one, the equivalence class of 4. Again, we'll just add 1 again, so we get negative 11, negative 6, negative 1, 4, 9, 14, 19. And if we go one more, what happens if we get the equivalence class of 5?
We have the equivalence class of 0.
Yeah. If you're 5 more than a multiple of 5, right, then you're a multiple of 5. So this is the same as the equivalence class of 0. And that makes sense because, look, we already saw that 5 was included in the equivalence class of 0. So here's like a really important fact about equivalence classes. If you have an equivalence relation on a set, the equivalence classes partition the set. That means two specific things. It means that everything in your set is accounted for, right? Every integer is in one of these sets. Also, they're disjoint. They're non-overlapping. So these sets don't have anything in common. So as soon as I see, if I want the equivalence class of 5, I go up here and I say, oh, 5 is in this equivalence class. So that means it's exactly the same throughout. If I want the equivalence class of 7, I just say, oh, 7's in this one, so since it overlaps in one element, overlaps in the whole thing. They partition the set. So a partition is just defined as, if I have some set, A, then a partition is a set of subsets of A, such that these different subsets are disjoint. They don't overlap at all. They're non-overlapping. And everything in your set is accounted for in one of those sets. That's what a partition is. As it turns out, once you have an equivalence relation, that means you get a partition. Also, if you have a partition, you can define an equivalence relation. You could see any partition as a set of equivalence classes for some equivalence relation on that set. And we're going to prove that. This will probably take the rest of our time, so we won't get to functions until Monday, I bet. This takes a little doing, but it's super fun. So a non-empty set of subsets, which we're denoting as angle brackets A, of a set A is a partition of that set A if and only if that partition, those set of subsets, is a set of equivalence classes for some equivalence relation. Something I'm going to draw your attention to here is that this is an if and only if. We have 2 proofs to write. We have to write both implications. This is why it takes a little while. We'll go this way first. If I'm going that way first, I'm going to suppose that I have a partition of A. So let's suppose that this set of subsets of A, so what we call our A1 or A2, right, or A sub I or A sub J, is a partition of A. So what I have is a set of subsets. And this consists of some subsets. I'm going to call it A sub I. And here, this is going to seem a little wonky, but where we say I is just some indexing set. More often than not, when you actually subscript things, we think of the index as being the integers, like the counting numbers. So like we have A1 and A2. But really, just think if we have some A sub i's, right? We're indexing these subsets. So we have a collection of subsets, and two things are true. One is that they're non-overlapping. So any A sub I, if you intersect it with another one of those sets, A sub j, that's going to be empty as long as I is not the same. As long as I didn't pick the same subset in the partition to intersect with itself. If I pick two different ones, they don't overlap at all. And the set A that we're working with is equal to the union of these A sub i's, meaning every element of A is in one of these guys. So this is what we're going to prove. Or we're going to prove that this partition, these sets, are equivalence classes for some equivalence relation. What we're missing is a relation at all, right? We don't have any relation to show that it's even an equivalence relation. So we're going to define it. Let's do this first. Let's define a relation R on A by the following. By saying that A is related to B, so that ordered pair is in the relation, if A and B lie in the same A sub I. It's really the only thing we have to go on is the fact that we have this partition. The only things at our disposal are these sets, these A sub I sets. So we've defined a relation. Now we need to show that this is an equivalence relation. And this is going to be, it'll be a bit of work because we have to actually establish the argument, but I don't think the argument is very hard to make. Like each of the three, like reflexive, symmetric, and transitive. So let's show reflexive. To show something's reflexive, we need to grab a single arbitrary element of our set. So let's let A be an element of A. We want to show that A is related to itself, but by the way we've defined our relation, we say that A is related to B if A and B lie in the same A sub I set. So I'm grabbing a single element A and I want to show that it's related to itself. Certainly, little a lies in the same, like A sub I, as itself, right? It's not going to be in a set and not in the set at the same time. So that means that A is related to itself. And this relation is reflexive. We want to show it's symmetric next. How many elements do we need to grab to show that something's symmetric?
Two elements.
2 elements, yeah. So let's let A and B be in the set A, and we assume that A is related to B. Right? We assume that we have the relation going in one direction. We want to show that B is related to A, right? We want to show that we can flip it. So AB is in the relation. What does that mean? What does it mean to be related? How did we define it?
A and B would have to lie in the same A by definition of the relation.
Mm-hmm. Yep. And if A and B lie in the same A sub I, what can we say about B and A?
You could say that, well, just as you could say A and B lie in the same sub I, you could say B and A lie in the same.
Yeah. Yeah, the two elements are in the same set, right? So that means BA is in the relation and R is symmetric. It's a similar argument to when we were talking about problem 2. Like if two numbers share the prime divisor, you know, if two integers A and B share a prime divisor P, then the integers B and A share that same prime divisor. Right? The order in which we list those integers doesn't change what its divisors are. The order in which we list the elements A and B doesn't change whether or not they lie in the same set. What's next? Transitivity. How many elements do we need to grab to show a relation is transitive? 3. So let's let A, B, and C be in the set A. And then we show we have two sets of relation, like two ordered pairs, right? We suppose we have A related to B and B related to C. We're going to do the same thing. The only thing we have to go on is how this relation is defined. So if A is related to B, that means that A and B lie in the same A sub I. And B and C, since that's in the relation, that means that B and C lie in the same A sub I. Now here's where we have to be careful. We want to say it seems obvious that A and C would have to be in the same A sub I, but it's not obvious. It relies on, like, we have to appeal to the fact that we have a partition. The partition, since these A sub I's are a partition of the set A, that means that they are not overlapping. If they overlap even just a little bit, they have to be the same set entirely. Because overall, like, sets can overlap a little bit. There's nothing wrong when you're just talking about sets in general, but by saying, oh, these two sets overlap here, but this set contains an element that this set does not have. We see that all the time. With a partition, that can't happen. They can't overlap a little bit. They either have nothing in common or they have everything in common. So since these A sub I's are a partition, and distinct A sub I's are disjoint, we would say, they're non-overlapping, then the fact that we have a single shared element, which is B, if they overlap just even at one element, they have to be the same A sub I. That's what tells us that A and C have to be in the same A sub I.
setup to this that that makes us say because distinct base of i's are disjoint.
Why can we say that? Is that what you're saying?
Yeah,
Because we started by saying, suppose we have a partition.
so by that.
And a partition, part of being a partition is that the distinct a sub i's are disjoint. They're non-overlapping. It's a set of sets that are non-overlapping, but account for the whole set. The whole set A. So we know A and C are in the same a sub I, and so A must be related to C. That means we showed that it's reflexive, symmetric, transitive. What does that mean? What does that tell us about R? Not a partially ordered set, an equivalence relation. Partially ordered set is anti-symmetric. The equivalence relation is symmetric. So as an equivalence relation, on A, whose equivalence classes are the a sub i's that partition A. So it's not surprising maybe that that there's this kind of I feel like I don't want to abuse the word equivalence, but there's this correspondence between having an equivalence relation and having a partition. It was sort of a natural way to define the equivalence relation. If you have a partition, just say, oh, two elements are related if they lie in the same a sub I, like partition set. You could just define the relation by using the partition itself. And as you saw here, we could, with a little bit of work, establish that it's reflexive, symmetric, and transitive. Questions on that direction? This was the first part of the proof. Right, so this was an if and only if. We have a little bit more to do. Okay. In the other direction, which we probably won't finish today, but we'll get a start on it. In the other direction, we are going to suppose that we have an equivalence relation that has some set of equivalence classes, and we're going to show that those equivalence classes partition the set. And the way we denote the set of equivalence classes is we put these square brackets around A and subscript it with R, or whatever we're calling the relation. So we'll just say that this set of equivalence classes is a set of like a sub i's, right? That's how we're defining those a sub i's. We want to show that those a sub i's form a partition of the set A. And if we're going to show that, we have to show two things. We have to show that they're non-overlapping. So that the intersection of two distinct a sub i's is empty. And that every element of A is accounted for. So A is the union of these a sub i's. But we get to use the fact that R is an equivalence relation. So that means what we get to use for free is that R is reflexive, symmetric, and transitive. We're actually going to show this second item first because it's easier. And then maybe we'll call it a day and do the first part one of that on Monday. So we'll just grab an element of A, of the set A. If we're trying to establish that A, the set A is the union of these A sub i's, all I need to do is show that if I grab this arbitrary element A, it's got to be in one of those A sub i's. That's all we need to establish. So what we have to use is the fact that R is an equivalence relation. If I've grabbed a single solitary element of A and I know that R is an equivalence relation, what is it I can state about A? What is a property of an equivalence relation that we could apply to a single element?
Reflexivity.
It's reflexive, and what does that mean in this context? Because R is reflexive. What does that allow us to say?
Go out on a limb here. I'll say, like, if there's an element, if there's like a pair of the same value within R, then R is reflexive.
Okay, so yeah, you're saying if every element's related to itself, R is reflexive. That's the definition of reflexive. But we know R is reflexive, so that means everything's related to itself. So what can we say about A?
It's related to A.
It's related to itself. Yeah. So we know that A is related to A, and now thinking about, it's an equivalence relation, which means now we're thinking about equivalence classes. If A is related to itself, that means it has to be in the equivalence class of A. It's contained in that equivalence class. A is an element of the equivalence class of A, which is one of those A sub i's. So no matter what element that I pick, I can put it in one of the equivalence classes because it's at least equivalent to itself. And that means that every element of A is accounted for. Fun?
Mind-blowingly fun.
The microphone wasn't on, but Andrew just said it's mind-blowingly fun. Getting a lot of agreement out there on Zoom. All right, so we know that every element of A is accounted for. What we'll do, we're running out of time, so what we'll do on Monday, the part one takes a bit of doing, so I don't want to get a tenth of the way through the argument. We'll start that part on Monday. We're going to show that two distinct A sub i's, two distinct equivalence classes, cannot overlap. That's basically all we have to establish here. And I say that's all we have to establish, but it'll take a little bit.
Yeah, you gave us extra pages.
I know, I was able to do this part. I didn't need the third page when I wrote it out, but depending on how big you write, I could totally see it spilling out onto a third page. So I decided to opt for more room than less. Okay, so we're working on assignment 2 that you could turn in on Monday. If you want me to look at a draft, just send it to me. Send me an email or something. I'm happy to look over your work and give some feedback. Enjoy the rest of your week. Reach out with questions as you have them.